Yeah, so this is joint work with Yuval Filmus at Technion. And yeah, the outline of this talk is going to be as follows. The first half, I think, is going to be familiar to most of this audience. Maybe the second half will be a bit more interesting. So the first half, we're just going to talk about kind of the usual algebraic techniques that one uses for showing the Erdős-Ko-Rado theorem. And then the second half, we're going to talk about what I believe is a new technique for showing the uniqueness in the statement of the Erdős-Ko-Rado theorem. So yeah, the second half will be what might be new stuff. First half is going to be just review of the usual sort of algebraic techniques in this area. So let's start by just establishing some notation. So bracket n is just going to denote the numbers from 1 to n, and choose k, the number of k element subsets of that. So family is intersecting. If I think we all know what that means, I won't bother belaboring that anymore. But the canonically intersecting families are going to have a special place in this talk. And so the canonically intersecting families are defined as follows. I'm taking all the k element subsets of n that contain a particular element of my universe. And so some particular I in the numbers 1 through n. Okay, so here's the Erdős-Ko-Rado theorem. All right, and so this was proven by Erdős-Ko and Rado quite some time ago. All right, so they actually proved something a bit more general concerning T intersecting families, and we'll get to those at the last slide of the talk. So this whole talk is going to be focused on just the intersecting, the one intersecting result, and so that's this theorem. Okay, and so like I said, the first half of the talk we're going to be talking about this this bound here, and the second half of the talk is we're going to be talking about the characterization of the extremal families. So like showing that F is in fact the only, so that the only maximum intersecting families are these canonically intersecting families that we defined up here. Okay, so there's many proofs of this, and this is sort of why I hesitated to say that the second, the proof of uniqueness that we're going to go through, I believe it's new, but there's so many proofs of these results that you have to be a little bit careful before you're claiming any novelty here. But I won't go into details about these other proof techniques. That they're all quite interesting, and a talk unto themselves. But as you might have guessed, we're going to be talking about spectral techniques. And as far as I know, I think Lovász kicked this off in 1979 with in some of his work where he was investigating Shannon capacity. And Chris also has, with his co-authors, has done a number of nice things in this area concerning spectral techniques, but different than what Lovász has done. Okay, so probably preaching to the choir here, but the framework that we're going to use for discussing this new technique for Erdős-Ko-Rado is the framework of association schemes. So, okay, so X is a finite set. We have these matrices A0 through AD that are binary, and we say they're a symmetric association scheme if they satisfy these 4 axioms. Okay, and so give you a moment to digest those 4 axioms, but so the consequence of these, if you satisfy these 4 axioms, is that we also have a dual basis of primitive idempotents. So, and each of these idempotents, you can think of these as orthogonal projectors onto eigenspaces, eigenspaces V0 through Vd. And so I'll denote the corresponding eigenspace for EI as VI throughout this talk. Okay, and so, and if you've seen some association schemes, recall that these primitive idempotents, we can write these as linear combinations of the associates, where we weight the associates by the appropriate dual eigenvalues of the association scheme. Okay, so the association scheme that's relevant to Erdős-Ko-Rado, of course, is this is the association scheme that everybody has probably seen before, and that's the Johnson scheme. And so it's defined as follows. And in the Johnson scheme, I would say that the associate that's received the most press would be the Kinesiograph. And so the Kinesiograph, this is right. So two things are connected if two K sets are connected if they're disjoint. Okay, so again, I think if you haven't seen this before, it's comforting to know that our friend the Peterson graph is can be seen as a Kinesiograph, and this image that I pilfered from Wikipedia certainly demonstrates this. So yeah, so we could ask the question, what are the maximum independent sets of this Kinesiograph? And so it's not too difficult to see that this is really the Erdős-Ko-Rado question in disguise, because if I have two K sets that are not joined by an edge in this graph, it means that they intersect. And so we have this graphical reformulation now of the Erdős-Ko-Rado problem. So classify the maximum independent sets of the Kinesiograph for all n and k, provided that k is less than n divided by 2. Right. So so cool. So we've reframed this extremal combinatorial question now as a graph theory question. And so what's the good in that? Well, we have the ratio, this well-known result called the ratio bound, which I'll describe now. So first, a little bit more notation. So 1 sub x is going to be the characteristic vector of the set x, and the Delsart-Hoffman ratio bound is the following. So if I have a deregular n-vertex graph with eigenvalues lambda, eigenvectors v, I can bound the size of a maximum independent set in terms of its eigenvalues and the number of vertices. Okay, and what's going to be crucial to this talk, so is this case of equality. So we have this condition. So if equality holds, then I know something about where the characteristic vector of this set lives. So in particular, 1 here denotes just the space of constant functions, and so this vector space over here, this is just the vector space associated to the smallest eigenvalue, the eigenspace of the least eigenvalue. Okay, so the second condition here is what is going to be crucial in this talk, because we're going to show how we can leverage that to prove the case of equality in the Erdős-Ko-Rado theorem. Okay, so right, so let's revisit the Kinesiograph now. So we're interested in the maximum independent sets of the Kinesiograph. So we can decompose, using the spectral decomposition of the Kinesiograph, we can decompose it as follows. So the lambda i's are the eigenvalues, and the ei's are the orthogonal eigenprojectors onto the eigenspace vi. Okay. So, and throughout this talk, I'm going to make ample use of the fact that this Johnson association scheme, we really know it completely. So this goes back to Delsart's thesis. We know what its dual eigenvalues are. So like it's a very nice association scheme in that regard, because it's certainly not the case for association schemes that are in same metric or co-metric. So we completely know this. We completely know this association scheme. So I can just take off the shelf what the eigenvalues are for the Kinesiograph. So I don't think that Lovász. So I think Lovász rolled his sleeves up a bit when he did this, and I don't think he used things that were known to Delsart. I could be mistaken here, but I think the way that Lovász showed it is a bit more of a tour de force. But what I'm sort of assuming throughout this talk is that we're using the Johnson scheme as just this, this known object, and so where we, we know everything, and so we're just taking things off the shelf to prove Erdős-Ko-Rado. So yeah, that's going to be the assumption throughout the talk. So right, okay, so we can clearly get at the minimum eigenvalue and we know the degree. So it's just a matter of plugging things in now to the Del Start-Hoffman ratio bound. And a little arithmetic shows that indeed f can't be larger than n-1 choose k-1. And that's exactly what we're looking for the Erdős-Ko-Rado theorem. And so this, it couldn't be simpler given that we know everything about the eigenvalues of the Johnson scheme. So right, so I think we can all agree that the bound for Erdős-Ko-Rado is, given the state of the art, is it's very simple. It's just a matter of plugging things into the ratio bound. And since we have equality here, we further know that this largest intersecting family that we have, it has to live in the direct sum of V0 and V1. Right. Okay, so I think we can all agree that showing the bound is for Erdős-Ko-Rado is nowadays is quite simple. So we're just plugging eigenvalues in. And for 2, I would argue that it's not quite so simple. So we haven't shown yet how do we characterize the canonically intersecting families, or how do we characterize the maximum intersecting families and show that the largest maximum intersecting families are canonically intersecting. And there really doesn't seem to be a simple spectral proof of this that I'm aware of. So there's a few methods that leverage the case of equality in the ratio bound to prove the uniqueness of the characterization of the extremal families, and I'm just going to describe some of these right now. So right, so there's one called I'll call this the rank method, and this appeared in Newman's PhD thesis under Chris Gotzel. And so we're going to let M be this this tall, skinny matrix whose columns are just the characteristic vectors of the canonically intersecting families. And what this rank method does is that it shows that it uses this matrix as the centerpiece, and argues that that any extremal family has to lie in the column space of this matrix. So in particular, you want to show that the column space spans V0 and V1, and then it takes some ingenuity to show that the only 0, 1 vectors in the column space are in fact the columns of M itself. And so this method is very versatile, and it's been used in a lot of results by Chris, Karen, Pablo Spiga, for objects that are for algebraic objects that are vastly more complicated than sets. So it's quite versatile, and it's sort of the only method we know for some generalizations of the Erdős-Ko-Rado theorem. So it's very nice in that regard. So later, Chris observed that this M matrix, well, we could actually squeeze a little bit more information out of it by considering the geometry of the rows of this M matrix. So we look at the convex hull of the rows of M, and this gives us a polytope. And so in particular, for the case of K-sets in Erdős-Ko-Rado, this is a very nice polytope. It's well understood, and you can check out Chris and Karen's book on the subject to see a more detailed treatment of the polyhedral structure of the rows of M. But you can leverage this additional structure to have a simpler proof that the canonically intersecting families are the only ones, and this even extends to T-intersecting families. So it's very nice in that regard. So these other ones, I won't. They're a bit more sophisticated, but I won't have a chance to really delve into them. But other ways that we could deduce that the canonically intersecting families are the only ones is by using results of Brouwer and I believe it's Brouwer, Gotzel, and Kulin. I can't remember, but yeah, we could we know what the dual width one sets are in the Johnson scheme, so we can sort of easily deduce this theorem. But that result is highly, it's not simple, and kind of what we're looking for here is a simple proof of that the canonically intersecting families are the only ones. And there's also some folklore in the analysis of Boolean functions, which is kind of this field that straddles extremal combinatorics and theoretical computer science, where they have their own results on what the Boolean functions are in this in V0, V1. So by Boolean functions, I mean 0, 1. So so there's definitely a few ways of showing this characterization, but what I would argue is that like none of them are like spectral per se. Like we have to go beyond the Johnson scheme in order to figure out in order to deduce the case of equality. And the point of this talk is just to give a simple spectral proof for step 2 here. So I want to use the fact that my maximum intersecting family lives in V0 and V1, and I want to use that to deduce that it has to be a canonically intersecting family. And I don't want to go beyond the Johnson scheme. I just want a simple proof of this fact in the spirit of the bound, right? Like the bound was quite simple. We just plugged in eigenvalues, and I want to give, we want some proof that's comparable in its simplicity to the proof of the bound. Okay, so that's the end of the first half of this talk. The second half, we're going to talk about how can we give a simple proof of this second point here. Cool. So I guess before we go to the next part of the talk, are there any questions about what was covered? Okay, if not, then we'll keep trekking forward. Okay, so right. So let's let P be the sum of the primitive idempotent C0 and E1. So this is just the orthogonal projection on the V0 and V1. Okay, and so V0 here, this is the space of constant functions, and so in V1, remember this is the least eigenspace. Okay, so right, it's expressions for the EIs are well known. So in particular, these like okay, so especially E0, right? I mean, this is by definition. But E1, maybe it's not so obvious how we could get this expression for the entries of E1, but it's really, in fact, maybe at the very end of this talk, if anyone's interested, we might be able to talk about this a bit more. But like it's once you know the dual, remember that E1 can be expressed as a linear combination of the associates and the appropriate dual eigenvalues. And we know these dual eigenvalues. And so really getting this expression for the ST entry of E1, this is just it amounts to just basic algebra. It's just, we're just rewriting things. And so, so this is, right. So these are the entries of E1, these are the entries of E0. And so they have a nice combinatorial meaning. And we're certainly going to leverage that. So a bit more notation. So if I have a family F in a element I can consider its restriction to I, and that's going to be all the elements of my family that contain I. Okay, we'll see what these restrictions have to do with the E1 here momentarily. So right. So for any family F and for any set S, we can write out what the S component of the projection of a family onto this the space V1 is. Sorry, that was grammatically awkward, but yeah. So maybe it's best to just read it and not speak it. So yeah, okay. So just plugging in this definition above, the only non-trivial step here is this last equality. So how did I get so how did I get here? Well, this is just double counting. Okay, so I'm now counting things from the vantage point of elements of S rather than from elements of the T sets of these elements of the family F. So right, so we just have some simple double counting that's happening here, and we see that this is where these restrictions come into play. Okay, so right, so yeah, the only thing that's happening here is double counting, and so if we look at the projection of any 0, 1 vector onto the space V1, we can write down exactly what it is, and that's really, yeah, that's really crucial here, that we can write this down exactly in terms of restrictions. And you know, these restrictions are going to be quite handy, because the restriction of a canonically intersecting, like let's say the ith canonically intersecting family, if I take the ith restriction of the ith canonically intersecting family, I should just get I get the family back, right? So it's the entire family, and so right. Okay, so there's one more ingredient that we need, so we can so we have a lot of control over the projections of 0, 1 vectors onto these onto the space V0, V1, and we just need another very rudimentary fact about the Johnson graph. So the Johnson graph is another associate of the Johnson scheme, and these are the sets that differ by just a single element. So right, so this condition down here, this is just a fancy way of saying, it's not even a fancy way, it's just the definition of being connected. So that's the only fact that we're going to leverage here from the Johnson graph, is that if I have a family, and if let's say I color the vertices of this graph with my family, there needs to be, I need an edge ST that where one endpoint's in the family and the other's not. Okay, so those are the only two ingredients that we need now to prove this theorem, that if I have a largest intersecting family, then it has to be a canonically intersecting family for some I. Okay, so let's start the proof. Okay, so we know that the Johnson graph is connected, so I start with my largest intersecting family and I pick S1 and S0 such that they are adjacent in the Johnson graph, and in particular, the element that S1 contains that the S0 doesn't is I, and the element that S0 contains that S1 doesn't is J. Okay, so I'm just picking, so that this follows from the Johnson graph being connected. Okay, so so remember that P is this projection onto V0, V1, which is the space of constant functions in the eigenspace of in the least eigenspace. So we know that this is where the characteristic vector of F lives. So when I project it, I just get the characteristic vector back. Okay, and so let's define PS1 to be just the S1th component of this projection, and we know that that's equal to 1. And PS0 is going to be the projection of S0, and we know that equals 0. By the way, we chose S1 and S0. Okay. So just using our projection expression, we can write their difference as follows. So we're just we're using the fact that we had that. So recall that projection expression, it was in terms of restrictions, and we had some constant term, but those constant terms cancel, and so this is what we're left with. So we're left with this really simple expression that's we're just running over elements of S1 and running over elements of S0, and we're just considering their restrictions. And we know that this has to equal 1. By the way, we chose S1 and S0. Okay, and so also we chose S1 and S0 to be super close. And so they're neighbors in the Johnson graph. And so that means that they have like these projections, a lot of these projections are going to cancel here because they have so many, they have k-1 elements in common. So what we're left with is we have a projection onto I minus a projection onto J. And just a little arithmetic here, we bring the n-2, choose k-1 over. Okay, so this is a really simple expression, and we're going to argue now that this restriction to fj, well, it can't be too small. In fact, it has to be kind of big. It has to be at least n-2, choose k-2. And why is that? So if it wasn't, and we took f and we threw away everything that contains j, I would have an intersecting family of n minus j, choose k. So this is recall our notation here. We're throwing away the element j from the set n, and we're taking all k sets. So for that domain, we would have an intersecting family, but its size would be greater than n-1, choose k-1, and that contradicts the bound that we've already proven. And so that's a contradiction. So this f restricted to j has to be at least n-2, choose k-2. Okay, and then once we've shown that, then we're essentially done, because we've shown that, so just doing a little arithmetic here. So we have f restricted to I, so we pull f restricted to j to the right-hand side. So we use that bound here, and so now we have that f restricted to I is this sum of binomial coefficients, and we all know what that is. It's just n-1, choose k-1. And so we are done. So that's the proof. And yeah, the ingredients of this proof, we just use the fact that we can write down what the projections are for E0 and E1. And we use the fact that the Johnson scheme was connected, and that's pretty much it. So yeah, so that's the proof for the original Erdős-Ko-Rado theorem. So are there any questions about that proof? And apologies, I'm not looking at the chat if there's anything going on there. But yeah, okay, great. So so I think like I said, like what constitutes simple and what constitutes like known, I guess, is all subject to interpretation. But I hadn't seen any proof along these lines for the case of equality. And we are heavily using the fact that the Johnson scheme is so well known, and we know its eigenvalues and dual eigenvalues, and that. So that's the grain of salt when we say a simple spectral proof. So we're definitely making use of some well-known and non-trivial results in the background, but it seems different to me. But anyways, yeah, well, so maybe let's see how this general technique can help us show results for other domains. And so since I'm the one that's giving the talk, you probably knew that was coming. Let's see if we can prove the Erdős-Ko-Rado result for perfect matchings in the same vein as for sets. Okay, so right, perfect matchings, these are just the perfect matchings of K2n. These are just sets of n disjoint edges that cover all the vertices of K2n. We're going to let M2n be the set of all perfect matchings of K2n. And so this 2n minus 1 double factorial, this is just the product of all the odd numbers that are less than 2n. Okay, so the canonically intersecting families here, these are these set families of, they're all the perfect matchings that contain a particular edge of the complete graph on 2n vertices, ij. Okay, so right, the object that replaces the Kinesiograph for perfect matchings is this perfect matching derangement graph, and it's defined in the same manner. Two perfect matchings are adjacent if they're disjoint, if they have no edges in common. And so this graph is like the permutation derangement graph. So there's an analogous graph one can define for permutations, and it's enjoyed a life of its own beyond Erdős-Ko-Rado combinatorics. It has interesting spectral properties and whatnot. And so you can Google around for that if you're interested. But the degree of this graph is it's the number of perfect matching derangements. And so it's the nearest integer of this this quantity here. Should remind you of the permutation derangement expression, only we have that root e there. And so that root e is actually going to really help us in this proof later, and we'll revisit that. But yeah, so we know the degree of the derangement graph. So if you recall, the ratio bound was, so the ratio bound holds for adjacency matrices of the graph in question, but it also holds for so-called pseudo adjacency matrices. And a pseudo adjacency matrix is just means that if I have a if I don't have an edge between sorry, let's see here. So if I don't have an edge between two vertices, then I can't have anything but zero. So so in particular, if you wanted to consider a subgraph of the graph in question, that would be a and you considered its adjacency matrix, that would be a pseudo adjacency matrix. And so that's what we're going to do for perfect matching. So I have this big complicated perfect matching derangement graph, and I'm not going to consider the whole graph. I want to restrict to a subgraph, and the subgraph is the Hamiltonian cycle graph. And so it's the graph where two perfect matchings are adjacent if their union is a Hamiltonian cycle, or a cycle on 2n vertices. And some basic combinatorics, you can show that the degree of this graph is 2n minus 2 double factorial. And this is the sum of all the even numbers that are less than or equal to 2n minus 2. Sorry, the product of all the even numbers that are less than or equal to 2n minus 2. Okay, so we're going to consider the adjacency matrix of this Hamiltonian cycle graph. And just to be sure we know what this graph is, and because I like this figure so much, maybe we'll take a quick peek here. So we have the rows and columns are indexed by perfect matchings, and these little diagrams here indicate the 15 perfect matchings of K6. And if we pick, let's say, this first one and this first row in the fifth column, and you were to glue these two perfect matchings together, you would see that I get a single cycle. Okay, and so this yeah, so this graph is actually another thing that's another object that's interesting unto itself. It's used in Erdős-Ko-Rado. We were able to use it in some other applications in theoretical computer science, and it's one of my it's one of my favorite graphs, I think. So anyways, this is the graph that we're going to consider. And this is the graph that we're going to plug into the ratio bound. So and some older work of mine using theory of symmetric functions, you can show that the least eigenvalue is negative 2n minus 4 double factorial. And so we have the least eigenvalue, we have the degree of the graph, and so now we can just plug things into the ratio bound. So there's 2n minus 1 double factorial vertices. 2n minus 2 double factorial is the degree of the Hamiltonian cycle graph. And right, and so we have the least eigenvalue here. You do some arithmetic and we get 2n minus 3 double factorial. And voila, that's the size, that's the size of a canonically intersecting family of perfect matchings, right? And so to see this last equality, you know, you fix an edge and then you take all perfect matchings so you take the, you fix an edge, you remove its endpoints from the graph, and you're left with k2n minus 2, and then you consider all the perfect matchings of k2n minus 2, and that's k2n minus 3 double factorial. So we also get that the largest intersecting family of perfect matchings now has to live in this this eigenspace, because we have equality that's met by the ratio bound. Okay. Sorry, equality is met in the ratio bound. Yeah. Okay. So yeah, maybe I'll slow down for a second. Do we have any questions about the bound? So I guess, yeah, like I said before, like these bounds, given that our knowledge of the eigenvalues of association schemes is like you know, ever increasing, like getting these bounds is easy. It's just a matter of plugging in eigenvalues. And so what we're going to shoot for here is something that maybe is not that simple, but still quite a simple spectral proof for showing that the largest intersecting families are going to be have to be these canonically intersecting families. Okay, but before we can do that, we need a little combinatorial proposition. So I won't get into the details of. I mean, it's not difficult to show this, but we're going to need a basic, just some basic combinatorics here. So if I have an edge ij, and I have this perfect matching W, and it's the case that W does not contain the edge ij, then if I consider all the perfect matchings of K2n that have the edge ij and also intersect W non-trivially, then that quantity has to be, it can't be it can't be too big. So in particular, so yeah, the only, yeah, so this one over root E, this is we're counting derangements here, and so this inequality here that we have, it's not tight. In fact, it's an overestimate, but it's all we need for proving the case of equality here for the Erdős-Ko-Rado theorem for perfect matchings. And so, you know, we should expect this, right? Because if I round up all the perfect matchings that contain the edge ij, then this is just a canonically intersecting family corresponding to the edge ij, and that has size 2n minus 3 double factorial. So if I also require that they intersect some W non-trivially such that W doesn't contain the edge ij, then the cardinality of this set should drop, and indeed it does. And so I won't get into the details of that proof, but it's really elementary combinatorics. And I know that's yeah, you shouldn't say it's elementary combinatorics. I don't mean that in the pejorative way. I think Igor Pak has a website dedicated to people that say, and the proof is just combinatorics in a pejorative term. So I don't want to end up on that list. So it's yeah, so it's you know, it's good combinatorics, and yeah, I'll leave it at that. Okay, so yeah, let's talk about the proof now for perfect matchings. So yeah, so okay, so we're going to do the same. So I didn't mention, right, so one thing that I didn't mention was this, the analog of the Johnson graph for the perfect matching scheme. But I think Sevi's done a good job of talking about this graph in this seminar. And some people call this the perfect matching flip graph, to where I take two perfect matchings and they're adjacent if they differ by a partner swap. And so what we're going to do here, we're going to take the swap graph, and we're going to use the fact that the swap graph is connected, and I'm going to pick M1 to be in my set, M0 to not be in F, and M1 and M0 are going to differ by a swap. And so what that means is that there's only two edges that they don't have in common. So this is a little bit different than before with the sets, right? Because then we had that they only had this difference had cardinality 1, so between M1 and M0. But here it has cardinality 2 because there's just due to the nature of perfect matchings. Okay, so we pick two perfect matchings that are adjacent in the swap graph. One's in my set, one's not, and they're pretty close. They have most of their edges in common except for 2. Okay, so in some previous work that I did, I computed the projection formulas onto the V0 and V1 space. So remember, V0 is the all ones functions. V1 is the least eigenvalue, the eigenspace of the least eigenvalue. And so this projection formula just comes from previous work that I did. And again, it's very similar to what we saw for the Johnson scheme. So it's, we're looking, it's like the take-home message here is that when we look at projections of 0, 1 functions onto these eigenspaces, V0 and V1, these we should think projections. Like there's a combinatorial interpretation of this, or sorry, we should think restrictions. There's like a way to describe this purely in combinatorial terms of restriction to particular elements of edges of K2n in this case. Okay. So again, we chose M1 and M0 to be super close. And so a lot of these, like most of the majority of these terms cancel. And what we're left with is this expression. And this is a little bit, so it would be nice if we could do the same thing here and be able to say something about the cardinality of these negative terms here. But this is where the combinatorics of perfect matchings and the combinatorics of K-sets diverge. If F is indeed say the canonically intersecting family Fij, then when I look at these restrictions, like FIL and FK, if I look at if I look at FIL and FKJ, these have to be 0, because there's no way that I can have a perfect matching that contains both the edge IJ and the edge IL. And similarly, I can't have a perfect matching containing the edge IJ and KJ because they share an endpoint. And so this is where the same trick that we use for K-sets, like arguing that these negative terms have to be kind of big, doesn't work because these can be 0. In fact, they will be 0 for like canonically intersecting families. So we have to do something a little bit. We have to do something a little bit clever here. But first, before we do something clever, let's clean up a little bit. So we've conceded that like these negative terms, they can't really help us. So let's just throw them out. So that's what I mean by tossing terms. And we're left with 2 positive terms that we're going to average. And so without loss of generality, we have this, we can say that the restriction to IJ is at least this big. Okay, and we've lost some like this averaging step. So we're dividing by 2 here. We've lost some we've lost something here by doing averaging. Like you can't, So we've still shown that the restriction to IJ is pretty big, but it's like, it's not tight like it was for K-sets. And so that's that unfortunately, it might seem at this point that we're stuck because we can't show that it's tight, but we're actually in luck. So we've shown that it's pretty big, and more than 1/2 of 2n minus 3 double factorial. So maybe in some change over here. So maybe in some loosely defined sense, we're halfway there. So what we're going to do now is like, we're going to suppose that F, our intersecting family, let's assume that it's not that it's not centered. That is, that there's some element of F that doesn't contain the edge ij. So this, in particular, this difference here, the set difference, is going to be non-empty. So let's say that there's a W that doesn't contain the edge ij in my set F. Okay. Now F is intersecting, so that means that everything in my restriction to Fi to ij, it has to intersect W somewhere. We know it can't intersect W at ij because W doesn't have ij. So it has to intersect W somewhere. And that's where that proposition is going to come in handy. So we know that by that proposition that it can't be any greater than 2/5 2n minus 3 double factorial. So that's just by the proposition. And well, we've shown that it has to be less than 2/5 n minus 3 double factorial, but here up above here, we show that it has to be greater than 1/2 to n minus 3 double factorial. And so that's our contradiction. So because of that, I mean, it must be the case that this difference here, F subtract the restriction to ij, that has to be empty. And if that's empty, then, well, it's a canonically intersecting family. And so that means that we're done. So here we needed a little, like, this averaging step that we took, we lost tightness, and so we had to do a little counting to save ourselves. And fortunately, so that the counting came in the form of that proposition. And like, for those that are familiar with these sorts of results, you can take this as like, the reason why this proof works is the fact that these so-called Hilton-Milner families for perfect matchings their cardinality is much lower than the cardinality of intersecting maximum one intersecting families. So that gap there is what made this proof go through. So if you know what that means, then that's kind of at a high level what's going on. But okay, so that was the proof for perfect matchings. So maybe to wrap things up, I'll talk briefly about an extension of the previous result. So we can generalize the previous result to perfect hypermatchings. And so I think maybe others in the audience, I think, prefer to call these things uniform partitions, but I'll stick with the hypermatching or the matching jargon. So let's let MK, Kn be the set of perfect hypermatchings of the complete K uniform hypergraph on Kn vertices. And so these are, again, just sets of n disjoint edges that cover all the vertices. We'll call these edges K edges because they all have cardinality K. So we say that two perfect hypermatchings, they partially two intersect if I can find two K edges, E and E prime, such that when I take their intersection, it's size 2 or greater. And this definition extends to families. So we say that a family is partially two intersecting if for any two members I can find edges E and E prime such that their intersection is greater than or equal to 2. So recently, Karen Marr and her colleagues showed for large enough n, if I consider a family that's partially two intersecting, then this family can be no larger than the following quantity. So just as a sanity check, if you replace K with 2, then we recover the previous result that we've been talking about for perfect matchings, because the complete two uniform hypergraph on 2n vertices is just K2n. And so this is a proper generalization of what we saw on the previous slides. And so what Karen showed with her colleagues was that the bound for an Erdős-Ko-Rado theorem for partially two intersecting perfect hypermatchings. Okay, so they conjectured that the canonically partially two intersecting families are the only ones that meet their bound with equality. And again, the canonically partially two intersecting families, these are just the obvious ones. Take your favorite pair of elements, I, J, and the set K, 1 through Kn, and take all perfect matchings, perfect hypermatchings that have an edge that contains both of these elements. Okay. So what we were able to show is that Karen's conjecture is true. And we showed it using the same sort of strategy, the same sort of techniques that we've been talking about in this talk. So we computed projections, and these projections can be framed in terms of restrictions. And for this one, we needed there was a little bit more arm wrestling needed to get the proof to go through, because the combinatorics here is quite a bit more interesting than what happens for the k=2 case. So there's some interesting combinatorics with hypergraphs, as we're all aware of, and so we needed more combinatorial results and a bit more. And the spectral argument was a little bit more fussy, but you can check out the arXiv post in the arXiv paper in the abstract that was posted for this talk if you're interested in how that proof goes. But it's using essentially the same method. And what's important here is that for this particular case of for partially two intersecting hypermatchings, if you were to try to do the other techniques, so mentioned way back at the beginning of this talk, so for instance, like the rank method or the polyhedral method. So the rank method seems really complicated to work with here. I mean, I tried it briefly, and I got nowhere fast. It would be nice if you could use a polyhedral method. I'm just about done.
Okay,
yes.
good.
Yeah. So the polyhedral method would be nice, but it turns out that this polytope is vastly more complicated than say the perfect matching polytope or the set or the polytope associated with the K sets. So this was like one instance where we really like this technique allowed you to circumvent like those obstacles. So it was, I guess could be another way to show it, but this technique was certainly appropriate. And that concludes the talk. So I'll just leave us with some open questions here, but thanks for your time.
Thank you, Nathan. Very nice talk. So is there any question for Nathan? Yes, Karen.
So I think your last slide here just answered the question I had. I was going to ask about the T intersecting. But do you need...
Yeah. So for T intersecting, it's it's, I don't know if these techniques could get it for Wilson's bound. So it's I mean, for if you make n sufficiently large, then sure. But I guess what was nice about everything that we talked about was that this holds for like the proper range of values. So it's so these Q analogs, even those, like you can use this technique, but there becomes a point where you like if, for instance, like if K is too large for like say the Q for like for the Grassmann scheme. So if K is too large, then these techniques no longer work. And it could be that there's a way to modify it, like these techniques to maybe use, so I'm just guessing here, but maybe if you use something more about the isoparametric properties of like the Q analog of the Johnson graph or the Johnson graph, then possibly you can make these sort of techniques go through. So we only use the fact that the Johnson graph and the Q Johnson graph, I mean, you're only using the fact that they're connected, but they have, they have stronger properties than that. So like, if I were to take my family and let's say I take my maximum intersecting family, I color the vertices, and then I look at the boundary of this maximum intersecting family. So I look at all the edges that have one endpoint in my family and one endpoint outside. Like there should be like there's additional structure there that you might be able to leverage to make these sorts of techniques go through. It's just that for T equals 1, we didn't even need to go so far. But I think that there could be ways of beefing up this technique to where you use more properties, in particular like isoparametric properties of these graphs to give you stronger assumptions. So yeah, it's an open question, but like I think it might be possible, but for now, just the naive method that I described here, it doesn't seem likely that such techniques will go through.
I think that you answered my second question sort of indirectly, because I was wondering about if you've tried a similar method when you have weird objects where you don't have this Johnson type relation, like you needed to pick two objects, one that was in the set and one that was out of the set, and they're as close as they possibly could be. But if you're looking, say, for intersecting blocks in a design, you'd never get ones that are different by one. But what you described about looking at the boundary, you might be able to add and subtract things in a way so that you'd still get your pretty little relationship.
Yeah, so it, you know, I haven't really thoroughly investigated that direction yet, but it's not implausible, I'll put it that way. But it seems like you could potentially leverage more information, like like we were talking about, and right, for these more exotic objects where you're no longer guaranteed such like where you're, let's call them perturbations, where you like things might differ by like be close in some sense, but still differ by many, like I don't know, atomic objects. So for instance, like so for these Q analogs, this is what seems to happen. Like you no longer like you can pick two things that are close, but suddenly when you subtract things, then you're left with like something exponential in Q, like that number of terms. And so it's and so for those cases, yeah, maybe picking more things along the boundary can help you. But yeah, so I tried to make this work for GLNQ and SLNQ and some of these other Q analogs of permutations. But yeah, for that, yeah, it fails for a good reason, and that's because there's multiple kinds of maximum intersecting families in that case, and so you wouldn't expect these techniques to work there. But yeah, I think this is an interesting direction to see if there is some way to make this technique work for Q analogs where you don't have this closeness that you do for combinatorial objects.